Hey everybody, and welcome back to Calc 3 Online. So today the plan is to actually talk about the integrals of vector valued functions, but I'm going to start off actually just doing another derivative problem. So this is actually out of the book, but it's a very good problem, and I thought we should do it. So the question is basically find f prime of 2. So this is f of t here. It's defined as a dot product between two vector valued functions. So it's not a vector, right? Because this is going to just be a function of t here. And they give you different parts here, and we're going to end up actually needing all that. So to start off, we're going to do f prime of t. And so this is just a dot product property. So you have u prime of t dotted with v of t. And then you're going to add to that, it's like the product rule, right, is all we're using. And then u of t dotted with v prime of t. Remember that the derivatives are just always on the outside like this. All right. And we know some of this. We know, well, okay, so we want f prime of 2. So that would be u prime of 2, dotted with v of 2 plus u of 2 dotted with v prime of 2. And we know some of this is what I really want to say. So we know u prime of 2. It's given right there. There's the other one. U of 2, we know that. We can get this just using v of t, and we can also take the derivative and plug into and get that. So basically, once we do all that and we plug everything in, take dot products and add them, we'll have the answer. So the parts I need are, I'm going to just kind of do this down here. So v of 2 is going to be, just plugging in 2, we're going to get 2, 4, and 8. And v prime of t is just going to be 1, 2t, 3t squared. So then v prime of 2 is going to be 1, 4, and then 12, right? All right. So now we can just go plug in, this here, and then we have that, and we have that, okay? So we're going to get u prime of 2 is, actually I'm going to do column vectors, I think, 3, 0, 4, and I'm going to dot that with v of 2, which is 2, 4, 8. Then I have to add to that u of 2, which is 1, 2, negative 1. And then v prime of 2, which is 1, 4, 12. Right. And I don't think I'm going to go through this a ton, but you can do this. Take the dot product, and then add those two numbers, right? So this is a number and this is a number, a scalar, right? If you do that out, you'll get 35. That'd be it. All right. So integrals of vector valued functions work basically like derivatives do. You just, if you want to take the integral of one of these, it's still a limit. Integral is just the idea of basically shrinking these rectangles down really infinitely small. And then they give you the area under the curve. And you can really just do it component-wise. So you can do it for the I stuff, the J stuff, and the K stuff. And that's kind of just same thing down here, right? So when I see something like this, if I just want to take the indefinite integral of it, I just go piece by piece. So I'm going to actually just stick it into vector form. So the integral of 2 cos t is 2 sine t. And then the integral of sine t is negative cos t. And then the integral of 2t is, we're going to go, bump the t up power, so t squared, and then divide by 2, so the 2 goes away, so we just get the t squared. And if it's an indefinite integral, this is the part that a lot of times gets students, you have a c, but your c is like a constant vector. So what I mean by that is it's basically a vector that's like c1, c2, c3. But yeah, it's a vector constant. These are just, c1, 2, and 3 are part of like the real numbers. But you do still need that. That is part of an indefinite integral for vector valued functions. But otherwise, it's really just doing like 3, integrals like normal. Just make sure you add a constant vector instead of just a constant. All right, so this problem is a good one because it uses what I honestly think is probably the most important thing you learn in BC Calc, and that is this little integration by parts technique. I taught differential equations for the first time last year, and I can't tell you how many times we needed this. It felt like every problem we just kept doing integration by parts. It is such an important technique to solving harder integrals. I have a little thing in my room here, and someday maybe you'll see it again. But it is a technique that we kind of use if we get stuff like this. And what I mean by that is really like a product, but a product of functions where you can kill off one of them via derivatives. So I'll go through this example and show it to you like in more detail, but the integration by parts formula that you learn up here, it actually, like all the integration rules really are just sort of have analogs to derivative properties, and this one is actually closest to the derivative, the product property. So if you do the derivative of this product, right, you get this. We've used that a few times recently, used it today. And then if you integrate both sides, right, you would kill the derivative there, you get that, and then you have the integral of all this. And then the integral of a sum is the sum of the integrals, so you can split it like that. And then all of this integral parts definition is really this statement rewritten, because they take f times g and they subtract over this one, and you have that. But I mean, this could have been rewritten a different way. It could be solved for f times g or u times v, whatever you want. But really, if you've never seen that, integration by parts is really just the analog to, like, it's the integral rule that goes with the product property for derivatives. And the way you pick it, I mean, the short answer is, so actually, let me just first explain this problem, and then we'll get into this part right here. So I want r of t, and I have r prime, and an initial condition. So this is one of those classic BC problems where you integrate, you use your initial condition, and you'll be able to like figure out what the original function was. Like you will be able to actually figure out this c. And so if I start off, right, the r of t will be, like the integral of t will just be 1/2 t squared. The integral of e to the t is just e to the t. It's this last part in here that we need to talk about, because that, when you take the integral of that, that's like a parts problem. And so I think I'll do that down here. So the integral of t e to the t, dt, is classic parts problem. Hopefully you did this one last year. But the way you do this is I always pick, you got this u du, this is how I always set up u du, and then I have dv and v. And so I want to pick u so that whatever u is, when I take the derivative, it goes away. That's the idea. It's kind of like you want to, you would not pick basically e of t to be u, because if you take the derivative, it would just stay e to the t. So you pick u with, really in this order is the idea. And this order kind of dictates, the best, from here being the top and this being the worst, the things to pick so that you can kill the u term with the derivative. Like exponentials would be horrible to pick because when you take the derivative, it just stays around. Like if you put e to the t here, it's going to be e to the t here. That's not going to help you. So I'm going to put t in here, and then du is just dt, and then dv is the rest of the stuff inside the integral, e to the t dt. So then if I integrate that whole thing, right, I'm just going to get e to the t. And then, so that, this is my u dv, right? And by parts, it says that this equals uv, which is t e to the t, and then minus the integral of v du. So e to the t dt, right? So this was my v du. And now this integral I can actually do. And that's only because I picked it so that this disappeared, right? I picked my u in the way where I could kill it with the derivative and it just goes away. So now that is a nice integral. I get t e to the t minus e to the t. And I can go and put that in up there, okay? Actually, I'm going to get rid of that now. So t e to the t minus e to the t. All right. And then plus some constant vector, right? So I took my integral of r prime, got r, but I have this constant vector. So this is where the initial condition comes in. I know if I do r of 0, I get 1, 1, 1. And so if I do r of 0 right now with what I have here, right, what I would get is I'd get 0, e to the 0 is 1, and then this term would get killed because I'm plugging in 0, so I'd have that term. So I would get e to the 0 is 1, which is but negative 1, right? And then plus some, like C1, C2, C3. So basically, what do I add to 0 to get 1, right? Because this is what we know needs to happen. And so you can see that C1 has to be 1, right? And then what do you add to 1 to get 1? Well, that's 0. And then what do you add to negative 1 to get 1? And that would be 2. So C3 is 2. So then r of t, I'm just trying to think about where to put this. Actually, I'm going to erase this. So I'm going to put C just over here. C is 1, 0, 2. And then I have room to actually write my answer. So r of t is going to be 1/2 t squared plus 1, right? Because I just added the 1 from c in there. And then I'll have e to the t, just plus 0, so e to the t. And then I'll have t e to the t minus e to the t plus 2. And so that is my final answer. That is r of t. Definitely make sure you know parts well. We'll definitely use it a bunch this year. And make sure you understand what this is all about. I think it's really important to know where it comes from, too. It just comes from basically taking an integral of the product property for derivatives. That's really where it comes from. All right. So this problem is just a Another integral, but it's got a lot of messiness to it, and I think it's just a good one to kind of get you warmed up back to how integrals work. We're going to do a ton more integrals this year, and it's a very important part of math, being able to do some of these weirder, kind of trickier integrals. All right, so it is just a... we're going to basically be able to do, 3 integral problems here. And some of them are really not too bad. Really, I guess I'm going to say one of them is not too bad. And that's the first one. So in the I hat piece, secant t, tangent t, the integral of that is just literally secant. Right? If you take the derivative... so maybe I'll add plus C1. So C1 just coming from the constant vector. So if you just take the integral of secant tangent, you get secant because the derivative of this is this. That's just kind of from a table of integrals, I guess. All right? And then for the j hat component, if you want to do the integral of t cos 2t dt. This one is another parts problem. So I would pick my u so that it disappears with a derivative. So I'm going to do t again. du is then dt. dv is just whatever is left over. So cosine 2t dt. And then v is the integral of cosine 2t dt, which you could do u sub if you want, but this is honestly just... kind of one I hope you sort of know. If you ever see, if we take the integral of cosine just t, right, we would get sine t. But in order to get rid of the 2 in here, we just divide by 2, because if you did, the chain rule, you basically would get the 2 on the outside, so we got to get rid of that. So we would have 1/2 sine 2t, and that'd be the integral of dv. Okay, so then this integral will equal uv, so t over 2 sine 2t minus the integral of v du, which is 1/2 sine 2t dt. And that, I'm going to just move that out. If you do the integral here, okay, it's kind of like this one that we did from dv to v, you would get minus cosine 2t, and then you would divide by 2, but since we have the half, basically it's like multiplying by another half in there, so we're going to get a negative quarter. But since this, so we're integrating sine, so this is actually going to have a double negative, because you're going to get a negative out of the integral of sine, because it's like a negative cos. And then you have another negative from here. So actually it's going to be a double negative back to positive. Now you're going to get a quarter, and then you're going to have cos 2t. And again, I'm going to do this kind of like plus t2, whatever my second component of the constant vector is. All right. Moving on to the last one. So k hat. For k hat, so I would do a u sub, because anytime you see the derivative of something, like if you have a statement like this, or expression like this, you see the derivative of sine in there somewhere, that's like your classic case for u sub. We don't have it here. It's like both of them will be like a product kind of case. But here there's a product where I can let u be a thing that's going to get killed with derivatives. Here, if I let u be one of these, I'll get like a cyclic thing where it just sort of pinballs back and forth between sines and cosines, with a negative sign in there somewhere. But because the derivative of sine is cosine, I can do u sub. So what I would do for k hat, in the integral of sine squared 2t cosine 2t dt, I'm going to let u equal the thing that has its derivative in there, so sine 2t. Then du is, you got to do chain rule, right? 2 cosine 2t dt. Then, so we kind of go here, and then I'm going to switch my problem to a u problem. So now I have, so actually, equivalently, du over 2 is cosine 2t dt, right? Because I don't want I had a 2 here, but I don't have a 2 up here. So I want to move that over. So I have a u squared, and then I have a du over 2 is what my integral becomes. And that's a much nicer integral. If you do the u integral, right, we're going to get u cubed over 3 times 2 is 6. And then I'm just going to switch back in my u equals sine 2t. And so I get sine 2t cubed over 6. And then plus like whatever the third constant, the third component of the constant vector would be. Whew, okay. So now I have like all the different parts. That one, this one, and this one. And the idea now, we have a definite integral, not an indefinite integral. And so basically I'll just go and evaluate each of these from, 0 to pi over 4. I'll just do 0 to pi over 4 and 0 to pi over 4. And that will let me then kill these constant terms. I won't need to actually worry about them, right, because it's a definite integral. And that's what I'm going to do on the next slide here. All right, so we have... Okay, we got all this. And so just plugging in 0 to pi over 4 on every little part from the last slide. We have, so I always teach trig stuff using this hand rule, but it's not something I can really show in remote like this. If you want, I can show you how I do these things, or maybe you just have the unit circle memorized, but somehow you need to be able to do this kind of nice trig stuff, really without a calculator at this point. So secant pi over 4 is... I just know it's, the flip of cosine of pi over 2, which is pi over 4, which would be root 2 over 2. So this is 2 over root 2. And then secant of 0 is just 1 over cosine of 0, which is 1 over 1. So that's just 1. So that's my first part. And then, here I've got the pi over 4 stuff plugged in to this. And then I already did the 0 plugged into it because this term with the 0 there, it kills it. And then the 0 here, cosine of just 0 is 1, so you get a quarter. And so a lot of this actually, it turns out nice because it's sine of pi over 2, which is what that is, and cosine of pi over 2. Yeah, these guys are going to be the nice 0 or 1 cases. So this one, cosine of pi over 2, is the 0. Yeah, I just blanked for a second. And sine of pi over 2 is going to be 1. And so then you get pi over 8 minus a quarter, which is pi over 8, I guess pi minus 2 is what I was thinking, over 8. Okay. Then this one, I just plugged in pi over 4 and 0, so pi over 4 and 0, and sine of 0 is 0, and so really this part goes to 0, and then this thing is the only part that's left over, and 2 times pi over 4 is pi over 2, And we just talked about that. That's just a 1. And so really all that stuff just simplifies to a 6. And so that big messy integral from 0 to pi over 4 of blah, 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 blah. I'm not going to rewrite it. Simplifies to 2 over root 2 minus 1. And then pi minus 2 over 8. And then 1/6. And then yay math, because that was a lot. Yay. Good. Yeah, but hopefully this problem is also just like a lot of good BC Calc review stuff. I do hope that you can do, all this trig fairly quickly in your head. I still mess it up, of course, sometimes we all do, but I hopefully, minus a few mess ups here or there, you can still do that in your head. And then I really do hope that U sub well and integration by parts, and then some of these kind of more straightforward like properties, like the integral of that is just secant. All right, and that is about it for integrals of vector valued functions.